Hello everyone, my name is Jiawei. Welcome to my presentation of our paper, Finding Optimal Modular Robots for Aerial Tasks. Different aerial tasks require flying robots of different designs to tackle. Without prototyping and testing, one hardly knows if a vehicle satisfies a task requirement. In our paper, Finding Optimal Modular Robots for Aerial Tasks, we apply computational geometry and optimization on a modular multi-rotor design to progressively generate and evaluate aerial vehicles that can satisfy any task requirement. Our methods are validated in realistic simulations. In an aerial task, the robot needs to interact with objects. For example, the vehicle on the slide interacts with the screwdriver. We abstract an interaction as the force and torque the robot needs to generate in its body frame. By stacking the force and torque vector, we obtain the range vector, which fully abstracts a requirement of the interaction. A task may contain more than one requirement of interaction. We define the set of all such ranges as the task requirements, T. With the mathematical abstraction of task requirements, we need to model a vehicle's actuation capabilities to define a comparison. Here, we focus on multi-rotor with fixed rotor directions. Since the task requirements are in the vehicle body frame, we explore the vehicle's capabilities of generating wrenches in its body frame. First, the rotor pulse determines how the input rotor forces are mapped to the robot range, which is captured by the design matrix A. Second, each rotor has a limited range of force generation, which introduces an element-wise range constraint of the input vector U. Note that M is the number of rotors. Considering the rotors are unidirectional, minimum is equal to 0, we model the actuation capability of the vehicle as the feasible wrenches, W, which is a set of all wrenches the vehicle can generate. Naturally, to check whether a vehicle satisfies a task requirement, we only need to verify that the set of required wrenches to generate in the body frame is a subset of feasible wrenches. The problem is, W is an infinite set. How do we compare the two sets? Note that W is the Minkowski sum of all column vectors of the design matrix A scaled by Fmax. An example is shown on the slide, where A1, A2 are the two column vectors that compose A, and W is the resulted Minkowski sum. Such a geometric observation shines lights on how we should compare T and W. By tightening the constraint on the input U for W to either 0 or Fmax, we obtain a new finite set S. An example in 2D and a realistic one in 3D are shown on the slide, where the red dots are elements in S and the polytope is W. We prove that the convex hull of S, denoted by HS, is equivalent to the feasible wrenches. Such a geometric equivalence allows us to transform the comparison into between two finite sets, T and S. We provide two methods. First, we check if all elements in T is inside the convex hull of S, which requires us to generate HS. Then compare the hull with each element in T. If all required wrench vectors are in HS, then the task is satisfiable. Second, without generating the convex hull, we could obtain the maximum magnitude of the feasible wrench vector that is on the boundary of W and is in the same direction of the required wrench vector. Then compare their magnitude. The two methods have different runtime complexities. The hull method works more efficiently when T has many, saying thousands of required wrenches. Now that we know whether a vehicle satisfies a task requirement, we would like to leverage modularity to progressively generate vehicle configurations for given task requirements. The general idea takes inspiration from social insects in nature. The group of simple modules reconfigures to accomplish different tasks. The modules we use in this paper are one type of the T modules introduced in our previous work on HMod quad. Multiple modules rigidly connect side by side to form a structure. To satisfy different tasks, we only need to reconfigure the structure or add new modules. Our method of generating a structure that adapts to the given task is referred to as the growing structure. For a given task requirement, we start with the structure of a single module. If the current design does not satisfy, we add one module to the current structure and examine all possible configurations until one structure is found to satisfy task requirements. As the number of modules increase, the number of configurations increase quadratically. In order to improve the search efficiency, we apply heuristics. The heuristic search keeps the center of mass of the structure at the same position. It makes the structure adds modules by pairs and ensures the structure is always central symmetric. For validation, we conducted simulations in Capella Sim. Results show that the two searching methods may give different structure configurations, but the robots are always able to generate all the required wrenches. In summary, in this paper, focusing on the versatility problem of aerial vehicles, we propose to use one modular multi-rotor vehicle design for different tasks. Via reconfiguration, the vehicle can adapt to different task requirements. We apply computational geometry to check without prototyping whether a configuration can satisfy a task requirement. Plus, we develop progressive search methods to find the configurations of the vehicle that satisfy a given task. Thank you for attending our presentation. We are open to any questions.